Hi, so in this screencast, I just want to briefly discuss Fugacity mixtures, essentially how we would say calculate values of my Fugacity using a cubic equation of state, what phase equilibria looks like using Fugacity and mixtures, and then how I might calculate phase behavior for, say, a binary system at vapor-liquid coexistence using a cubic equation of state. Okay, and so some refreshers from our last set of notes is using our definition of Fugacity. Okay, so partial molar Gibbs free energy of component I at, say, Tp and Yi minus G bar I, okay, not, okay, some reference state value. So my reference state needs to be at the same T, but it need not be at the same pressure, and it need not be at the same composition, is by definition equal to RT log Fi at Tp and Yi relative to Fi not at the same T, but not necessarily at the same pressure and composition. Okay, so for an isothermal process, difference in my partial molar Gibbs free energy gives me RT log ratio of fugacities. Okay, so this state, so G bar I, okay, and Fi correspond to the partial molar Gibbs free energy and fugacity at the same state. G bar I naught and Fi naught correspond to the partial molar Gibbs free energy and fugacity at the same state, which we typically take to be, say, our standard state, right, or our reference state, or it could just be any old given state, but those are at the same state. Where things change for fugacity mixtures, okay, is for the case of an ideal gas. Okay, so the fugacity of component I in an ideal gas mixture is equal to not pressure, but it's partial pressure. So YIP or just PI. Okay, and so in terms of fugacity coefficient, okay, so just like for pure component systems, the fugacity coefficient of component I is by definition the fugacity relative to that of an ideal gas. Okay, and to kind of expand this out, this would be the fugacity of component I at Tp and Yi relative to the fugacity of component I in an ideal gas mixture at the same T, P, and Yi, right? The same temperature, pressure, and composition. Fugacity relative to that of an ideal gas at the same conditions, okay, gives me my fugacity coefficient. Okay, and for completeness, my fugacity coefficient is also by definition at that same Tp and Yi. Okay, so fugacity coefficient still defined as fugacity relative to that of an ideal gas. Okay, only now my fugacity of an ideal gas is going to be equal to partial pressure, Yi times P. Okay, and so a common practice, right, and say we'll use when we write out our criteria of phase coexistence, is if I know the fugacity of component I, right, or I take the fugacity of component I, and then typically what's common is to what I would call expand it out, right? So I'm going to expand my fugacity relative to an ideal gas standard state or an ideal gas reference state, which is this guy down here, and we'll talk about in a second what that means. But I expand it out, so I expand it out as phi times Fi ideal gas. Okay, so in general, it's correction factor times idealized state. So I expand out my fugacity as being correction factor times fugacity of corresponding ideal state, which in this case is phi times Yi times P, right? So I expand my fugacity as correction factor times that of an idealized state. Okay, so if I can assume, say, that my state is an ideal gas, well then Fi is just YIP, my correction factor is just 1. Okay, good, beautiful, right? See that ideal gas limit, Phi is just equal to 1. All right, okay, and so I guess this is just kind of me talking at random, but how would I go about computing, okay, Fi? Okay, now the key is when we talk about like computing fugacity, everything we did back in chapter 7 for fugacity of pure component systems essentially applies here. Okay, again, the only real difference is in the ideal gas limit, the fugacity of component I in my ideal gas mixture the fugacity of component I in an ideal gas mixture is equal to partial pressure, right? The pressure that component I would exert if all of the other molecules are deleted from that system. Okay, when we had a pure component system and there's only one component present, the fugacity of that component in an ideal gas was equal to P. Okay, when it's a component in a mixture, it's not P, it's Pi, the partial pressure. Okay, but otherwise we use all of the same tricks. Okay, and then one last note before I forget. So remember, G bar I, partial molar Gibbs free energy. Okay, comes up a lot, and so we also give it this term mu I, right? We also call it chemical potential, right? It comes up so often we name it its own special thing, chemical potential, mu I. Okay, so in terms of computing Fi, okay, so the most common approach, especially when using a cubic equation of state, would be, okay, well, by definition, I have that G bar I, okay, minus G bar I naught is equal to RT times log Fi over Fi naught. Okay, so the most common approach would be, well, let's take our standard state or a reference state to be an ideal gas, okay, at the same conditions. Okay, so that this becomes G bar I minus G bar I ideal gas at the same conditions. So this would be at Tp and Yi. This would be at the same Tp and Yi. That'd be equal to RT log Fi over Fi ideal gas. Okay. Well, if I look at the left-hand side, this just becomes the partial molar residual Gibbs free energy. And I look at the right-hand side, that just becomes the RT log fugacity coefficient. Okay, cool. Okay, so why this is a value is G bar I residual. Okay, remember G is equal to H minus TS. So G bar I residual is equal to H bar I residual minus T S bar I residual. Okay, and so why this is of use is via an equation of state we've worked out expressions to get H bar I residual and S bar I residual. So if you think back to not chapter 5, right? So chapter 5 dealing with pure component systems, right? We worked out expressions for the molar residual enthalpy and molar residual entropy for a pure component system. Okay, so you could just as well work out expressions for the partial molar residual properties in an ideal gas mixture, right? What's going to be key to computing these accurately, though, would be the quality of your mixing rule, right? The ability to come up with an accurate mixing rule to describe my system. Okay, but in theory, I could calculate these two quantities via a cubic equation of state. And so then that would give me a way to calculate G bar I residual, the residual partial molar residual Gibbs free energy via an equation of state. And so if I can calculate this, then I can calculate RT log Phi. Okay, and if I can get, Phi, well then if I want F, right, Fi would just be Phi times Yi times P, right? And so, if I wanted to calculate these using a cubic equation of state, I would need to know, say I want to calculate fugacity in a given mixture, at a given temperature, pressure, and composition. Okay, the easiest, most straightforward case. So if I think back to when we worked with cubic equation state for pure component systems, okay, for pure component systems, our inputs to our black box to calculate properties via an equation state were temperature, pressure, and then Tc, Pc, and omega, right? And you could use any two intensive variables. You could use, say, temperature and volume, but T and P are the most straightforward, okay? And so we're going to work with those. And so for pure component system, I specify temperature and pressure, and then I know Tc, Pc, and omega for that pure component, and I can get molar volume of that system. I can get residual enthalpy, residual entropy, whatever I want. Now here, when I have a mixture, in addition to T and P, okay, so say I have a binary mixture, I'll need temperature, pressure, and then the mole fraction of one of those components of my mixture. So say Tp and Y1. Okay, so those would go into my black box along with Tc, Pc, and omega for each component. Okay, so then with all of that information, and I know the composition, and I have some magical mixing rule, out could come H bar I residual and S bar I residual. Okay, and so I could get, then log phi from that. And so then once I have, phi, I just multiply by yi times p, which I know those were inputs to my black box, and I could get f if I wanted to. Okay, cool. Okay, the other way you could go about it is just like we played with in chapter 7. Okay, is if 1. Okay, if I'm thinking about differentials, if I play with just this expression here. Okay, so remember these two states are at the same temperature, right? Okay, just in general, when I define my fugacity, these are states at the same temperature, right? Isothermal processes. So that would tell me then that the differential, okay, and let me bring RT over here, of G bar I residual over RT is equal to the differential of log phi I. Okay, all right, now I'm going to need a real memory jogger. Okay, so let me come back to this one in a second. Okay, I'm going to come back to here in a second because you'll see the connection in a moment. Okay, the other thing I do is if I just come back up to my definition of fugacity, okay, and I can take, so I'm going to come back up here and I'm going to divide by R2 or RT, and then I'll play with log rules. So I could take this expression, okay, and I could rewrite this as G bar I over RT minus G bar I naught over RT is equal to log Fi minus log Fi naught. Okay, so these both just correspond to standard state values. So if I were to compute the differential of the two sides, okay, then I would have the differential of G bar I over RT is equal to the differential of log F. Okay, so this is for an isothermal process. So if I think back to my differential of dimensionless G from chapter 5, okay, memory jogger. Hopefully I get it right. You might have to check me on this. But we had the differential of G over RT was equal to negative H over RT squared dt, I think, minus I think V over RT, okay, dp. Okay, so you'll need to fact check me on this to make sure I'm right. Okay, but I'm thinking this is it. Plus V over RT dp. Okay, so what that would tell me then is for an isothermal process, dt is 0. Okay, so differential log F then, okay, I would get then the differential log F would just be, okay, so now this is partial molar, so it'd be partial V bar I over RT, okay, dp. Okay, and again, you're going to have to fact check me on this, okay, but I think it's V bar I over RT because if I just think back to G, dg is equal to negative SDT plus VDP. We're again for an isothermal process, that's 0, so dg is V dp, so it should be dg is V over RT dp for that isothermal process, right? That should be the same. Okay, so I think I'm right. Okay, so I could get an expression for the differential log F would be partial molar volume over RT dp. Okay, and so why I said I would come back here is then, I could say differential log phi I would be V bar I residual over RT dp. Okay, then V bar I residual over RT, so that would be partial molar volume V bar I minus partial molar volume of an ideal gas at the same conditions. Okay, and you have to look back to how we did that back in that chapter. But how I want to say we tackled that is that V over RT I could rewrite as, so equation of state for real fluids is PV equals ZRT, so that V over RT is equal to Z over P. So I could write that as Z over P dP. And so then, you could go that route, right? So for the case of an ideal gas, C is equal to 1. Okay, but again, how you would typically go about this is where you typically go about this is just relating g bar I residual to RT log phi, because this I can calculate via an equation of state. Okay, cool. Okay, then the last kind of two notes we want to make is, let me insert a new page. Okay, two notes is, phase coexistence. Okay, so let's talk about phase coexistence. So phase equilibria. Okay, so let's imagine I had a binary system at VLE. Okay, so phase coexistence, I still have chemical and thermal equilibrium, equality of temperatures and pressures. And then chemical equilibrium I could write as an equality of the chemical potential of each component in each phase is equal, or the fugacity of each component in each phase is equal, right? And there really is no, derivation. If you want, a derivation that these are equivalent, here's my attempt, right? So if I had, say, mu I vapor is equal to mu I liquid, okay, I could just as well write that as mu I vapor minus mu I liquid is equal to 0. Okay, and so, since I have a difference in chemical potentials or partial molar Gibbs free energies between two states at the same temperature, that's by definition RT log Fi vapor over Fi liquid. Okay, so it must be that is also equal to 0. Okay, so it must be then, so I could divide by RT, that log Fi vapor over Fi liquid is also equal to 0, and therefore, taking the exponential of both sides, Fi vapor over Fi liquid is equal to 1. All right, you could equivalently say Fi vapor is equal to Fi liquid, right? So you can replace your equality of chemical potentials via an equality of fugacities, an isofugacity equation. Okay, so if I had a binary system at VLE, okay, so what that would look like then is I'd have F1 vapor is equal to F1 liquid, F2 vapor is equal to F2 liquid. Okay, and then typically what would happen is you would expand your fugacities. Okay, so I would expand my component 1 of the vapor as V1 vapor, Y1 times P is equal to liquid phase, V1 liquid, X1 times P. Okay, and then for component 2, V2 vapor, Y2P is equal to V2 liquid, X2, and P. So the pressure of the two phases are equal, so we could kill that. And if you wanted to rewrite it, you could rewrite it as V1 vapor times Y1 is equal to V1 liquid, X1, or V2 vapor, Y2 is equal to V2 liquid times X2. Okay, cool. Okay, so this is a little different than when we had a pure component system. Say component 1 was the only species present in the two phases, and we ended up with an equality of fugacity coefficients. Okay, cool. All right, so binary system at coexistence, we have an equality of fugacity coefficients of each component in each phase, and here's me just expanding them out. Okay, and a spoiler alert as we move ahead. Okay, this is always going to be the case in general, but what typically happens is, performing our expansion of our vapor phase fugacity in this way is typically, the approach we'll take, right? So here we're essentially taking our idealized state to be an ideal gas, right? This is correction factor accounting for deviations from ideal gas behavior, right? It's related to my partial molar residual Gibbs free energy. But typically, expanding our liquid phase fugacity with respect to an ideal gas isn't always the best, right? It works when we're working with the cubic equation of state, which has issues due to mixing rules. And so in general, we'll adopt or take as our idealized state an ideal solution, and we'll talk about that later on. Okay, cool. All right, so then the next thing I just want to kind of talk about is, okay, here's our isofugacity equations. Okay, let's talk about calculating phase coexistence using a cubic equation of state. Okay, so now the general idea will be, okay, let me try and sketch, say, a pxy. Okay, so the approach will be the same whether I'm trying to, say, calculate a pxy or txy for a given binary system. Okay. Okay, so if I sketch my pxy phase diagram, here's my straight bubble line. I have some curved dew line. Okay. All right. So now the okay, and t is fixed. So the general idea would be, if I want to construct a pxy phase diagram for a binary system using a cubic equation of state. Okay. First, okay, what I would have to do is I would look up, TC, PC. Okay, my parameters would be TC, PC, and omega for each component. Okay, so that's piece of the puzzle 1. Piece of the puzzle 2 is you better have a good mixing rule. Okay. All right, and then, in this case for pxy, t is constant. Okay. T is constant or fixed. If you had a txy, then p would just be constant or fixed. Okay, so then the general strategy is, okay, I'm going to imagine mapping out my pxy phase diagram one point at a time. Okay, so then the procedure would be, okay, you're going to say loop over x1 values from 0 to 1. Okay, so in a given iteration, you fix the value of x1. So say I want to calculate, I'm going to look at, so this is my bubble line here. So I'm going to say look at x1 of 0.1, okay, and for the x1 of 0.1, I want to solve for p, and I want to calculate y1. All right, so I want to fix x1, and for that x1 and that t, I then need to calculate p and y1 for that system at coexistence. Okay, and then it's just a matter of easier said than done. Okay, so I fix x1, so now I know x1 and t. What I don't know are y1 and p. All right, so what I need to do is I need to find the value of y1 and p so that my isofugacity equation is satisfied. Okay, all right, so I know x, I don't know y. Okay, how does p factor into this? Well, these fugacity coefficients. All right, so I calculate my fugacity coefficients as partial molar residual Gibbs free energy of each component in each phase. Okay, how do I get partial molar residual Gibbs free energy? Via my cubic equation of state. Right, so for given x1 and t, you would essentially think of it as, say, guess a value of p and y. Okay, because then once I have p and y, I can then go to my cubic equation state, plug into my black box, calculate partial molar residual Gibbs free energy of each species in each phase, right? And by each phase, if you have a reasonable estimate that puts you close to coexistence. So you calculate, so you guess essentially y1 and p. You could use that in your black box to calculate your fugacity coefficients. Then you check to see if those are the fugacity coefficients that solve your isofugacity expression. If not, guess again, right? And I say you guess p and y, and in theory, it's not quite so easy, right? But that's the general idea. So calculating coexistence using cubic equation state, so it can be done. Okay, to actually do it numerically is rather complicated. Okay, where it's complicated is that systematically, guessing, say y and p, and then getting convergence. Okay, so that part's difficult. In terms of getting these things accurate, the difficult part there is the accuracy of your cubic equation of state, which is dependent on your mixing rule. Okay, and we'll play around with that for project 2. Okay, so calculating VLE using a cubic equation state is doable. That's in theory how you'd go about it. In the book, they talk about some strategies to actually performing the numerical calculations. But key is, in theory, you could do it, but numerically it's pretty complicated. And then the accuracy is ultimately going to be dictated by the accuracy of your mixing rule in your cubic equation of state, which is a problem all of its own.